Rob is a faculty chair, and he has investigated various aspects of theoretical physics, including string theory, quantum gravity, and gravity. And today he's going to tell us about the collisions of renormalization, holography, and entanglement. So please start.
Okay, well, thank you for all coming. I know it's a very strange title. Titles are not my forte. And I played with a few others before I chose that one. So I wanted to share some of those with you. So one of the other ones on my list, which is now just a subtitle, was Curious New Mashups from String Theory. And, well, this is a tough crowd, man. I don't know what I'm going to do. If you don't like this, just go to sleep. I mean, in any event, so that's not the only thing you remember about the talk. Another more provocative title that I came up with was The Coming Revolution. And so what I'm trying to convey to you, I'm not going to do anything technical, but there are various ideas here. And what we're finding is, as Takeshi said, is there are interesting overlaps between these. And I'm using the word collision because collision's a good physics word. And as the picture here conveys, it's a very exciting time if you're in the middle of the collision. Unfortunately, this is what I think many of you are reading when you read the title. And so part of the talk is I'm going to have to give you a lightning introduction to all three of these ideas. And then I'll also try and talk about the overlaps and what perhaps the implications of those overlaps might be in the longer term. But first I wanted to go back to this word, collisions. This is one kind of collision. What are the kinds of collisions that I'm thinking about? Well, it's really a collision of ideas. And this is something that's really shaped theoretical physics in the last century. This was a time when we saw collisions between all sorts of different kinds of ideas, and they came together to produce fruitful new insights and new perspectives on physics. And so just to be clear on the kind of collision we're talking about, I'm going to focus on this corner of the diagram. And so here we've got a couple of topics that we all know from our undergrad physics. Physics 101, we learned about circuits, magnets, and the culmination of the 19th century physicists' work, which were the four laws that Maxwell wrote down governing the electric and magnetic fields. In the other corner over here, we've also got another Physics 101 topic. We've got four more laws. They're very, very different. The form, the language is very different. The beasts that they're supposed to describe are also very different. So what does this have in common with that? Well, we all know that if you heat things up enough, they start to shine. And so in investigating this behavior here, what people discovered was the ultraviolet catastrophe. And ultimately, that gave us yet another perspective, or led physicists of the day to develop a new kind of physics with a new kind of equations, a new way to look at the physical universe. And it's something then that gave us new insights into the behavior of materials and matter in general. But it's also something that shapes much of our modern culture here in North America. So these are the kinds of collisions I'm talking about. But this is a warning, this slide, which is that what I'm going to be talking about is that we're now in the middle of a collision. And so this picture evokes a time when we were in the middle of another collision, namely this collision between thermodynamics and electromagnetism. And we were trying, or these gentlemen and lady here, were trying to understand what the implications or what the meaning of quantum mechanics really was. And so the question I have for you is, are any of these people really happy? And the answer is, well, by the faces, well, there's one gentleman here who's pretty happy because he's going to win a Nobel Prize in a couple months after this, and he's ready to party. But the rest of us, or the rest of the people in the picture, are confused. They're struggling with these new ideas, And ultimately, it led to marvelous things, as I described. But when you're in the middle of the collision, it's a time as much of confusion as it is a time of enlightenment. And so the collisions that I'm talking about today are really emerging from our attempts to go beyond the bottom of the picture here. It's part of the project that string theorists are involved in trying to unify gravity or general relativity with quantum field theory. And so ultimately, I'll come back to that at the end of the talk. But as I promised, for the most part of the talk, what I'm going to be talking about are these ideas, the renormalization, the holography, and the entanglement. And as I've drawn it here, these, in this Venn diagram, what it's supposed to evoke is that each one of these topics is something that is part of the common language in various fields of theoretical physics and influences much of the thinking in those fields. But then the Venn diagram, again, is supposed to describe the idea that we're finding common ground between these different ideas. And so I'm going to make a lightning tour of the Venn diagram to describe not just the topics, but also give you an idea of what's in the overlaps. But let's get started at the top here with renormalization, or the renormalization group. And, oh, I see, okay. I upset my computer. Yeah, I give that away. Okay, so what is renormalization? It's a very simple idea. It's the idea that often we have a system with microscopic constituents, but they can come together and produce new collective phenomena on macroscopic or much larger scales. And so the renormalization group is something that packages that in a mathematical language. And it really reveals something very interesting or fundamental about physics, which is that the physical or the behavior, the phenomena at large scales is largely insensitive to the details of the physics of these microscopic constituents. And that's actually a very important result. This is why physics works. It's why I can describe this water, the flow of that water, without coming to grips with quantum gravity or nuclear physics or even atomic physics. There are a few parameters, say temperature, density, or a flow velocity, perhaps viscosity, that I use to describe this physical phenomena here. And it's largely, well, one never even addresses the fact that we know at some level this water is composed of, 10 to the 23rd microscopic atoms or molecules that are moving around or zipping around to form that water. So here, well, here's a little cartoon that describes our luck. This is not the way the real world works. Rather, we have this universality. Now, one of the successes or one of the keys here is that I can do this effective description with just a few parameters. It's something that has the renormalization group has a long history going back even to the 19th century and discussions of turbulence. The context in which I'm going to be talking about it is really applying it in the context of quantum field theory. Quantum field theory, as you may know, is something where when we start calculating too hard, we run into various infinities, and so people had to come to grips with these infinities that said, basically, we didn't understand how the quantum field theory behaved at very, very short distance scales or very high energy scales. And so this was really perfected with the help of various condensed matter ideas in the 1960s. And we now have, well, the renormalization group as a textbook, or at least a graduate textbook topic that we all learn about. And so there are some parameters in our quantum field theory, and as we integrate out the short scales or the high energies, those parameters slowly shift in a way that this mathematics describes. And so here's my parameter space, and if I start here and I integrate out some energy, the arrow indicates that my parameters will move through the parameter space along the blue lines. Now, in the picture, though, there are a set of special points that I've marked in red. The red, all of the blue lines either start or end on one of these red dots, and those are places where this flow ends or is stationary. And so those are very special quantum field theories. Those are known as conformal field theories or CFTs, and these are field theories with just a few dimensionless coupling constants or parameters that characterize all of the behavior at this point or say at that point. And those are very special theories that will appear at several points during my talk, and so I wanted to point them out here. The idea that there are special quantum field theories where there are only a few dimensionless parameters and no intrinsic scales. So that's my lightning introduction to the normalization group. The next topic, or the next one around on our Venn diagram, is holography. Now that's a word in the common parlance, and it's something that evokes a lot of different images to all of us. But this is not the image or not the context in which I'm using the word. Rather, I'm using the word in the context of gravity or perhaps quantum gravity. And it's an idea that came out of Hawking radiation, or Hawking's realization that black holes are not just black, but rather they slowly leak and emit radiation that looks thermal. And a consequence of that, which Hawking and Bekenstein before him developed, was the idea that the horizon actually carries an entropy. So this is a rather remarkable fact. This black hole actually has an entropy that's encoded into the geometry of the space-time. But I've written out this formula in full with all of the constants here to indicate that one of the, well, this is a rather remarkable formula that provides a crossroads, again, between many different areas of physics. We have the speed of light here, evoking special relativity, Boltzmann's constant for thermodynamics or perhaps statistical physics, Planck's constant for quantum theory, and of course Newton's constant because it's a discussion of a gravitational system. And in fact, here we see side by side quantum and gravity, and so this formula or this effect was often seen or thought to be a window into the nature of quantum gravity. And certainly in many contexts, reproducing this formula from some microscopic picture is seen as a benchmark for some tentative theory which is going to combine quantum theory and gravity together. One of the things this shows us, though, is that when I combine all of these constants from nature, that we're provided with some fundamental length scale, namely the Planck scale. And so what this formula is really doing is it's measuring the area of the horizon in units of the Planck scale. And so one of the things to emphasize here, though, is that that's a really, really, really small scale or a small distance, something like 10 to the minus 35 meters. And that might compare with the resolution of what's man's best, or the best man-built, human-built microscope, namely the Large Hadron Collider, which has a resolution of down to 10 to the minus 20 meters. So this is some 15 of orders of magnitude even smaller. And this being small means that I get very large entropies. As an example, we can turn to our local star, the sun. That's a big bag of hot gas, about 700,000 kilometers in radius, with temperatures ranging from a few thousand degrees at the surface to tens of millions of degrees in the interior. And one can, or if you're me, you can look it up on Google and you find that the entropy of the sun is around 10 to the 58, an impressive large number. However, if I take that big bag of hot gas and I squash it down to a radius of about 3 kilometers, I'll form a black hole, which Mr. Hawking tells us has a temperature of roughly a few nanokelvin, or tens of nanokelvin. And because this is so small, in fact, now I get an entropy that's almost 20 orders of magnitude larger than the entropy given by the sun. And so this is just an example where we see how large the entropies that we're talking about here really are. The Boltzmann's constant sits here unashamed in my formula, and it reminds us that entropy was invented by people who were thinking about steam engines and were worried about losses of potential work. And so this formula originally came up in discussions that were called black hole thermodynamics, or when people thought about various black holes participating in various processes and described them in a thermodynamic way. It's also, though, entropy in most systems is known to have some kind of statistical origin or interpretation. And so this also evokes the idea that black holes, there are some kind of complicated, in fact, many, many complicated microstates that somehow come together to build this macroscopic object. It's really in that context of the microphysics or the microstates of the black hole that holography arises. There, the conjecture or ideas put forward by 't Hooft and Susskind originally was that the horizon not just encodes the details of these microstates or can count these microstates, but it actually can describe the dynamics and the evolution of those microstates. So I can describe this three-dimensional object by an effective theory that lives on the horizon or on this two-dimensional surface, and hence the name holography. Now that was a lot of conjecture and speculation for a long time. It was made more concrete in string theory with the advent of something known as the ADS-CFT correspondence. So what is that? That's really just a dictionary. It's a dictionary that says there's a certain set of physical phenomena which I can describe with two different languages. One of those languages is the language of a conformal field theory, or the CFT up there. So what I'm using there is the description of a quantum field theory. It's a quantum field theory without any scales. It's only got dimensionless couplings. And in particular, there's no mention of gravity in this side of the dictionary. But the other language is a language of gravity. In fact, here I'm supposed to be using or describing quantum gravity with a negative cosmological constant. Hence, the simplest solution of Einstein's gravity with a negative cosmological constant is anti-de Sitter space, and hence the ADS label on that side of our dictionary. The remarkable thing is that this is a theory, a conformal field theory in d space-time dimensions, whereas this is a gravity theory in d+1 space-time dimensions, and hence the holography. Here we have a description of this physics in the bulk in d+1 dimensions in terms of a theory, a quantum field theory with one less dimension. Now that's worthy of an entire lecture or course in and of itself. The one thing I want to add here is, or a simple question you might ask is, why do I need an extra dimension, or what does the gravity theory do with this extra dimension? And it's a rather simple idea that on this side I said that this is a theory without any scale, and so in some sense it's a self-similar theory, or I can find excitations at all different energy scales that are similar in a well-defined way to the excitations at other energy scales. And so what the gravity theory is doing is it's organizing those excitations, or those degrees of freedom at different energy scales, using the radius in the extra dimension. So if I'm probing gravity degrees of freedom here at a large radius, what I'm doing on this side of the dictionary is probing short scale physics or high energy physics. Similarly, if I'm looking at stuff, excitations in the bulk here down at small radius, I'm looking at low energy excitations in the CFT. And so there's this idea in this holographic picture that radius and energy scales are related on these two sides of the dictionary. So what does that have to do, or how can I relate that to RG flows? Well, I said this is a system that organizes things by energy scales, but it's precisely what RG flows were talking about. They were talking about integrating out energy or degrees of freedom at different scales and producing an effective theory at low energies. So if you remember the diagram, there were different kinds of CFTs connected by these blue lines. And so how do I get a theory, not just a one CFT, but several CFTs? Well, rather than coupling gravity to a constant, I couple it to a scalar field. If this has a nice or an interesting potential, it might have different fixed points or different stationary points. And if I sit at any one of these, that provides a negative energy density here. Just by fiat, in my construction, I've made sure that the potential always has a negative energy or gives a negative energy density. So if I'm sitting at any one of these points, what I described so far is I have gravity coupled to a negative cosmological constant, and that has a dual or an equivalent description in terms of some CFT. The cosmological constant is different for each of these, and so in some sense, the CFT, the conformal field theory, is going to be slightly different to describe each of those. Now, an RG flow, a renormalization group flow, was something that connected different fixed points or different CFTs. And so here now we have a simple model, and so there's a simple idea. How do I get from here to here? Well, I start with a solution where the scalar field is sitting here, and it basically rolls down the hill and ends up down there. But this rolling is something that it's going to do in radius. It's not a rolling in time, but rather at large radius in my geometric description, I'm going to have the scalar field sitting near this value, and so the physics is going to look like the physics of this CFT. As I go down in radius, I'm going down to lower energy scales, and eventually at the middle of the space, I end up down here at this value. And so in the infrared or at low energy scales, the theory behaves like a CFT associated with that geometry there. So essentially what I've done is I've geometrized, or I've provided a gravitational description of this picture. Each one of the red dots corresponds to one of these critical quantum field theories. In the geometric or gravitational language, there's a corresponding anti-de Sitter spacetime. And the blue lines that connect the dots are just more interesting geometries that interpolate between one ADS region and another ADS region, going from large radius down to small radius.
What does this let you calculate that you couldn't calculate?
Sorry?
What does this let you calculate that you couldn't calculate before?
What is, well, there's a whole story there that typically the kind of quantum field theory that I'm describing in this language is a strongly coupled field theory, and so conventional quantum field theory techniques aren't going to apply. And so when we go to this other language, I find that there's this gravitational language, but it's one that happens to be for various, well, there are many details, but in many cases I end up with a weakly coupled gravity theory or a gravity theory where I can calculate. And so I get new insights into the behavior of the quantum field theories with these gravitational calculations.
Near these fixed points?
Sorry?
Generally near these fixed points? Or?
Yeah, I mean, the idea of a holographic RG flow here is sort of a footnote in if I was teaching a course. Most of the time what we're doing is we're focusing on the behavior near a certain fixed point or near a particular CFT. So I gave you an idea of renormalization group, holography, and what the common ground is here. You may have noticed a date that said this was something we understood. Well, these RG flows were something we understood very soon after the invention of the ADS CFT, and so it goes back to the years 99 or 2000 that this part of the story was understood. Entanglement is an idea that, again, we may have heard the words, and what it evokes is EPR, Einstein-Podolsky-Rosen paradox. What quantum entanglement, if I want a definition, it is if I have a quantum system with many different parts or many different degrees of freedom, there is a single wave function that describes all of those different parts. And implicitly then, the behavior of the different subsystems becomes correlated just because of that structure, that there's a global, or they may become correlated because of the global structure of the wave function. The context where Einstein and friends discussed it was where I have an atom here that simultaneously emits 2 photons, and the measurements of Bob here and Alice over here, very far away, are always correlated no matter how far apart the photons go. And so they referred to this as spooky action at a distance. They actually were studying this or presenting this as a way to disprove quantum mechanics or to show that there was an inconsistency there. Now we understand that this entanglement is not an inconsistency, it's a feature of the quantum world. It's something that really distinguishes the classical world from the quantum world. And so it's actually become front and center, say, in quantum information theory, where entanglement is really a resource for various manipulations, such as computations or secure communications. It's also being understood now in condensed matter physics that certain phases of matter or certain phenomena, that the key idea that distinguishes them from, the simple phases of matter that were studied before is the quantum entanglement of the underlying degrees of freedom, in particular, typically the electrons. And so people talk about quantum Hall fluids or unconventional ITC superconductors, and there's also quantum spin liquids and a host of various associated phenomena with those systems. Now, here I gave something that you may recognize as the singlet wave function, or this is supposed to represent the wave function for these 2 photons in this experiment that reveals the entanglement. One might think, well, I can make it more entangled by making the wave function more complicated and adding extra bits to it. But in fact, what you find if you study that wave function is that the spins are not entangled at all. In fact, this is a product state, and the spin here or the polarization here doesn't care at all about the polarization there. On the other hand, if I take that wave function and then just flip a simple sign right there, it turns out that I produced an entangled state.
Is there a log of EPR classically in the sense that entanglement is just referring to really averages in subsystems, and so you can imagine having a big reservoir in 2 systems, and that there's sort of classical probabilistic correlation between them, which as the systems move apart, that would still remain? Or is there something that says that it's because of the phase aspect of these entanglements, only they are the significant ones that exist?
Yeah, well, it depends how far you want to carry the analogy. I mean, a lot of the words... a lot of the words that I use or throw around for entanglement, you might apply in that context. You might imply it just for the description of waves. But to really make headway, where did I go? I went the wrong way. To really understand or to make use of entanglement in the way that I do, say, in quantum information, it really is important that it is a quantum system and it is this global wave function that I'm yeah.
But the thing, I mean, entanglement, it always has sort of the spooky element to it, but the rigorous definition of entanglement is just you know, where you're dealing with subspace.
Right.
And so that is ubiquitous in physics, always was.
Okay.
And maybe features of it had not been fully understood, but people have been working with it forever.
Yeah, no, I mean, I think what you're saying is we deal with correlated systems all the time. And, yeah. No, yeah. I won't disagree with that.
Well, I'm just trying to remove a bit of spooky from this, because that's just the nature of the world we live in, but it was also the nature of the classical world we lived in.
Well, the spooky aspect is when you find people that don't follow this.
Why don't we save this discussion for later and carry on?
I was just trying to say, I use entanglement all the time, and it's generally for a non-quantum system.
Okay. What I was going to say, or where I was going, is if I give you wave functions with two polarizations or two spins, it's easy to fool around with them and decide when I'm describing the spin in an entangled state or when they're not in an entangled state. But generally, well, the topic of today's discussion is systems with lots of degrees of freedom, and that's not a practical way to approach the problem. And so what we need is a diagnostic that tells us when a system is entangled or when subsystems are entangled, when they're not. And perhaps to give us a measure of that entanglement. And so that's what, where entanglement entropy comes in as the hero of the day. Here what I'm going to do is I'm going to use entropy as a measure of correlations between subsystems. And so the procedure is very simple. I take my favorite quantum system, divide it into two pieces. I trace over or integrate out degrees of freedom in half of it or in one subsystem. What's left over is described by a density matrix. Given a density matrix, I evaluate trace rho log rho, throw in a minus sign as von Neumann instructed. And in this particular context, that's called entanglement entropy. And so in this simple case, we can go through that exercise, or you can go through that exercise as a homework assignment, and what you find is that the entanglement entropy is log 2, or that there's 1 qubit's worth of entanglement. Applying the same procedure here, you find that the entanglement entropy is 0. There's no entanglement between the two polarizations. And in this case, with the extra funny sign, I go back to log 2's worth of entanglement. So this is one diagnostic. It's one of many that the quantum information folks have developed to try and understand the behavior of more complicated quantum systems. And so that is the idea of entanglement. What I next want to show you is that there's what's in this patch here between holography and entanglement. And it goes by the simple name, holographic entanglement entropy. So this was our diagnostic of entanglement, and this is saying that that has an application or an appearance in a holographic context, or in particular in the ADS CFT context. So what is my favorite quantum system going to be? Well, again, it's going to be quantum field theory. I have to divide that into two pieces, and so what we do is we take a Cauchy slice or a time slice, and you simply divide that into an inside and an outside with some arbitrary boundary. I integrate out the degrees of freedom in the outside or in region B. I have a density matrix then that describes what's left over in the interior, and I apply my favorite formula. And so I can suggest this as a starting problem to a grad student, and before they've even started the problem, I know what the answer is going to be. The answer is going to be infinity. And the problem is with quantum field theory that this calculation that I've described is dominated by short distance correlations in the vicinity of this boundary or the entangling surface here, the blue line. And so to make sense of it, I have to regulate the problem, i.e. what I do is I'm going to throw out all of the degrees of freedom below some short distance. So I'm going to introduce a short distance cutoff. That's going to be the delta. And if I do the calculation in that context, what I find is that the answer is organized in powers of some large macroscopic scale that characterizes this region over delta, my short distance cutoff. And the powers here are controlled by the dimension of the space-time. So if we live in 4 space-time, 3 space and 1 time, then this would start with an r squared over delta squared. This looks like just a constant, but in fact what it does is it turns into a logarithmic divergence. But I'm a string theorist, so I also like to think about d being arbitrary. I can have d equals 10, and then I have more interesting series here. Now, one of the interesting properties that was revealed is if I do this calculation not for one boundary, but I do the same calculation for the same quantum field theory and the same regulator or the same cutoff for many different boundaries, I find that all of these terms have a geometric interpretation. And in particular, this first term I can interpret as the area of the entangling surface, or the blue boundary, over delta to the appropriate power. So in 4 space-time dimensions, that really is an area with an r squared over delta squared. So this is an idea that goes back to Raphael Sorkin. And what he noted was this peculiar property, that entanglement entropies grow like the area rather than growing like the volume of the region enclosed there.
It to be like a convex surface, because I can imagine giving it many, many wiggles so that you boost its area sort of arbitrarily high while still maintaining the same volume. And then you wouldn't necessarily expect the entanglement to go up by making the area wiggle.
No, in fact, I would, as long as your wiggles are macroscopic, by which I mean the scale of the wiggles is larger than this cutoff. In fact, you will find that the entropy grows bigger and bigger, even though...
The surface bound in the same volume will give a higher entropy.
Yeah. Or, yeah, this first term grows with the area. So how does this apply in holography or in ADS-CFT? Well, there I said I had a quantum field theory, namely this boundary conformal field theory, and so I can draw a picture, and this is now a picture that applies for the CFT. This is really, though, a picture that lives at the boundary or at the edge of my ADS space, and so what I'm imagining is down here is the rest of that bulk geometry, and this is somehow r equals infinity in some cartoon sense. And the trick is that while I hinted that this is a really hard calculation to do in quantum field theory, but does holography give us an easy geometric or gravitational interpretation of that same calculation? And that's something that these two gentlemen showed us in 2006. And the rule they came up with is I take all of the surfaces that hang down here into the bulk, but reach up to the boundary to touch this entangling surface, the blue line. And then what I do is I evaluate the Bekenstein-Hawking formula on this surface in the bulk, and I extremize, I minimize this quantity, and that picks out a special surface down here. But that extremal value here is, or it corresponds to the entanglement entropy in my in the other side of the dictionary, in the quantum field theory, where I'm evaluating entanglement entropy between A and B. So that's a rather interesting result. At least it has the, I'm not going to go into it. This is a hot topic of research that lots of people are investigating. But at least it has the flavor of an entropy in that this formula, although originally it arose in the context of black holes, this was a formula that told us about the entropy of horizons. Here we're not studying a horizon, but again, this has the flavor of an entropy at least. And here we're turning it into a particular kind of entropy or a particular calculation, or we're replacing a calculation in the boundary theory with this gravitational calculation.
When you do the calculation from the CFT side, you must get infinity.
Yes.
So you're talking about the finite part of the entropy?
Yeah, there's, I promised no technicalities, but yeah. Why am I going to get infinity? Well, I said this was a picture, this picture lived out at r equals infinity. And so if I try and evaluate this area, integrating all the way to r equals infinity, it's going to diverge. And why is it diverging? Well, it's diverging because of all of the contributions at large radius, which is contributions coming from high energy scales in the CFT. So that's not a bug, that's actually a feature of the calculation. But you're right, to do this properly, I then have to introduce a regulator in the geometry or in the gravitational description, and there's a whole song and dance, but that's something that's under control.
Does the scaling work if I make inverse delta go like
You're hinting at something else that appears on slide 54, but let's wait till slide 54. The only thing I wanted to add is my friends Shinsei and Tadashi actually won a prize, the New Horizons Prize, just last month, and they were cited for their work or this proposal, which came as a real surprise. And like all surprises, we basically ignored them for 6 or so years, and it's only recently that we've become to appreciate how marvelous this formula is. Okay, so what do we got? Well, we've gone all the way around the diagram. We filled in this, or I gave you a flavor at least for this overlap, and now a flavor for that overlap. But it leaves us with one here, entanglement, the overlap between entanglement and the renormalization group. What could possibly go in there? Well, here again, we can look back. And there's a rather prescient paper by one John Preskill at Caltech. So John's was a particle physicist, but he became interested in quantum information theory. And 99 is the time when quantum information was actually, it had become a well-established field of study. And at the time, it was regarded, or it looked basically like a new branch of computer science. Now, John was in a physics department, and I think perhaps he was a little bit nervous that he was doing computer science, or actually, I know John wasn't, but I think John's postdocs were nervous that he was leading them down the trail to become computer scientists and not physicists. And so he wrote this paper that described what he thought would be some interesting ways in which quantum information theory might give us new insights into difficult physical problems. And one of the topics that he brought up in that paper was something called the C-theorem. And this goes back to work by one Zamolodchikov back in 1986. There's a lot of details here, but what he was studying were these renormalization group flows for theories in 2 space-time dimensions. And what he showed was that there was a lot of elegant structure that actually we basically get for free in that context. And it all centers around this constant, his C function, that lives on this space of couplings that I described before. And so there are various properties and lots of definitions, but I won't bore you with that. What I'm going to say is that this was our picture, or my picture, of renormalization group flows with the flows connecting the critical points. What Zamolodchikov's picture does is he turns it into a landscape. Essentially, what this C function does is it gives an altitude, or provides an elevation for all of these different theories. And it also, what his work shows, is that the RG flows always go downhill. And so as I move from this high energy fixed point to, say, this low energy fixed point, I always have to be traveling downhill. And that tells me that there isn't going to be a flow that connects this point with that point over there, because there's no way that I can get, well, between those two while going down all the time. Similarly, there's never going to be a flow that gets me from here to here, because that would be taking me up in this altitude defined by the C function. It's called the C-theorem because if I evaluate this quantity at the fixed points, what I just told you is it's always going to be bigger here than at the low energy end of the flow. And so at the fixed points, or in the CFTs, it becomes a quantity that characterizes the properties of that CFT. And so for any flow connecting a high energy or a UV fixed point to a low energy or infrared fixed point, CUV is bigger than CIR. And so that's a simple corollary of all of this elegant structure that Zamolodchikov introduced us to. So what does that have to do with quantum well, John's idea was that somehow here what I'm doing is I'm integrating out, I'm throwing away degrees of freedom, and so that has the flavor of losing information. And so he thought that maybe the tools of quantum information can give us a new insight here. In fact, that insight came from this gentleman and this lady in 2004, and they wrote a paper which rephrased the C-theorem using entanglement entropy. And so this is a very short, or relatively short paper, and it tells us something profound about quantum field theory, but if you look at the paper, there are no actions or correlation functions, no S matrices, the kinds of things that I expect to see in a quantum field theory paper. Rather, they're just using some basic fundamental principles and a new idea that's known as strong subadditivity. And it says that if I have a system and break it up into many different pieces and put the pieces together in different ways, as I've indicated here, then the entropies associated with those different subsystems satisfy this particular inequality. So using that and basically Lorentz invariance and doing a lot of geometry and boosting and pushing things around, what they show at the end of the day is that this C function is always bigger at the high energy end of a flow than at the low energy end of a flow. And so they rephrase Zamolodchikov's proof or result in terms of the entanglement entropy. So this is a rather remarkable result, and again, it was one of those results that everybody just ignored for many years, and it's only recently that we've come to appreciate what these folks did. What were the particle theorists or the high energy theorists doing? Well, what they were interested in was the question, what Zamolodchikov worked with were two-dimensional quantum field theories. Is there something similar that applies in higher dimensions if I, for instance, look at four-dimensional quantum field theories? In that context, well, to make a bridge, one should try and understand what the role of C is in the quantum field theory. So what this is saying is that in a conformal field theory, if I evaluate the trace of the stress energy tensor, it's typically 0. However, there's a slight anomaly, or it's not quite 0 if I put the conformal field theory on a curved space-time. Rather, I get something that looks like this. So here's the Ricci scalar, or here's something about the geometry, and the coefficient here has that C in it. I can play the same game for conformal field theories in 4 dimensions. There's more complicated geometry, and in fact, there are 3 different parameters, or 3 different central charges. And so the question is, does any one of these 3 satisfy a similar C-theorem when I'm studying RG flows? It turns out there are counterexamples that rule out 2 of them, and there's only 1 left standing. And it was actually John Carty who suggested that, well, he didn't know that these were ruled out right away, but his conjecture was that this quantity here, this central charge known as A, should satisfy something like the C of the two-dimensional theories. And so there was a lot of interest in that. There was lots of interesting examples in perturbative quantum field theories and supersymmetric gauge theories. There was also some study of this using the holographic RG flows. And you can see the dates here go back again to the turn of the century. You know, after this supersymmetric work, progress really stalled and no proof was really found. And in fact, what's hidden in the ... is a counterexample was found. And so nobody was interested in this idea for a long time. But what I want to tell you is that, in fact, just recently, there's been a resurgence of interest in these ideas. And in fact, we've seen rapid progress. So this is a part of the story where I made some contribution. What we were doing was we were studying these holographic RG flows, but in more complicated theories of gravity. And so what we found was there was a quantity in the gravity theory that satisfied this nice C-theorem in any number of dimensions. You can tell this is the gravity theory because here's the Newton's constant, here is the ADS length scale or curvature scale, and then there are various other parameters, alpha, lambda, mu, which are couplings in our gravity theory. And so you have to solve this cubic equation, plug it in here, and you get some formula that is, you know, several pages long. But what our result is that if I evaluate that at the large radius or high energy end of a holographic RG flow, it'll always be bigger than at the low radius or low energy end, small radius, low energy end of the flow. And so, well, this is a complicated expression, but it's an expression in the gravity theory, and we were puzzled and we stared at it for a while to try and understand what is it telling us about the dual theory, about the quantum field theories that are behind this. And one of the things we found was that in any even number of dimensions, you could relate it to a very special coefficient that appears in this trace anomaly, or this, here I'm evaluating the trace of the stress tensor in some number, well, it could be 4, 6, 8 dimensions, and it arranges itself in an interesting way. There are various geometric pieces, but there's a special geometric piece that's topological, and the coefficient there is called A. And what we found is that this quantity here with these funny normalizations is precisely this A in that formula. And that actually agrees with John's work, or John's conjecture. His conjecture actually doesn't just apply for 4 dimensions, but for any number of dimensions. He was actually focused on that particular coefficient. So we, in our holographic studies, we're confirming or agreeing with John's work.
More about what happens in the bulk as you flow from UV to ion.
Basically, what I've got is some complicated gravity theory coupled to a scalar field. The scalar field has some potential. And so at the large radius, I'm sitting near one fixed point of that potential. And as I move in radius, I flow down, or I roll, the scalar rolls down to another fixed point. And so what I'm doing is I'm comparing what this evaluates to if I just sat at that fixed point or the scalar just sat at that fixed point.
And what's this topological data on your spacetime? Is this some, because ADS has some topology, are you changing?
Oh, yeah, no, I'm not changing the topology. This is just a comment on the combination of curvatures here correspond to the thing that I would integrate over my d-dimensional, my boundary spacetime to get the Euler character of that space.
Okay.
But that topology is sort of in the boundary theory. This is bulk stuff.
And I had one more question
Yeah.
about these spacetimes. So you're solving this. You're taking the trace of the conformal field theory, I guess, stress energy on these spacetimes. Is the curvature of these spacetimes fixed by hand from the outset, or is it somehow self-consistently found by coupling to the matter that's there? I guess if you see what I'm trying to say. So normally
okay, so again, this is in the boundary theory.
Right.
There's no gravity in the boundary theory. And so you can put curvature there. I can do that by hand because there's no gravity. And so I can evaluate, I mean, there's a prescription that tells me how to do this.
Well, but for the C-theorem, you're in a two-dimensional CFT, right? So there you also had the trace being formed under the Ricci scalar.
Right.
Was that still the Ricci scalar of the two-dimensional?
Of the two-dimensional theory, right.
And so is that curvature you just place and work with, or is it
Yeah.
somehow
Yes.
self-consistent with the quantum fields, the matter content?
No, there's no gravity, and so there's no back reaction of the quantum fields on the geometry. But that's in the boundary theory. There is a theory of gravity lurking in the calculations, but that's a different set of, yeah, okay. So we stared at this for a long time, and what we came up with after a couple months was that we were able to identify this with a universal contribution to the entanglement entropy in a particular configuration where I had a spherical boundary or entangling surface in my boundary theory, and I evaluated the entanglement entropy there, and I looked carefully and I picked out a particular coefficient, and it turned out that that was what this coefficient matched up to. Now, being bold or silly, one or the other, we said, well, this is some really complicated thing that works so marvelously in holography. Our conjecture is that it should be something that applies more broadly. It should be a universal feature of quantum field theories, even ones that don't have a holographic description. So then, as an aside, the following year, our friends, or some of our friends in Princeton actually were doing some similar work, well, they were actually studying supersymmetric gauge theories, and they came up with something that was the equivalent of a C-theorem in 3 dimensions or any odd number of dimensions. And it involved evaluating the partition function of the quantum field theory on a spherical geometry, yada, yada, yada. But they came up with some C function, and they came up with the clever name of calling this, rather than a C function, an F theorem, or a C theorem. It was an F theorem because it was related to something that looked like a free energy. Now, in fact, independently, before they had done this, I had written a paper with these folks here that said that this entanglement entropy approach that Aninda and I had put together and this free energy approach would in fact give us exactly the same results. And so that this was another way to probe the C-theorems that we had been talking about. And so what this was doing was actually giving, from a different perspective of purely quantum field theory, either in supersymmetric and some non-supersymmetric contexts, evidence for this new C-theorem for 3-dimensional quantum field theories. And in fact, my friends went on the following year to basically soup up their 2-dimensional proof, and they came up with a proof of the F theorem using the entanglement entropy. And so these pictures are just supposed to convey that the geometry gets more complicated, but it's basically the same or a very similar idea that by using the geometry in these pictures, unitarity of the quantum field theory Lorentz invariance, and this property of entanglement entropy, strong subadditivity, you could come up with a proof that this was obeyed by any quantum field, or should be obeyed by RG flows of any quantum field theories in 3 dimensions. And then another note is that they were also, for this work, awarded a New Horizons Prize just last month. I also have to add that there was progress in 4 dimensions. We now understand that the A theorem is a true theorem, but this work by Komagardsky and Schwimmer actually did not rely on entanglement entropy, and so our understanding here uses a different technology coming out of quantum field theory, although there are some hints on how you might apply or put together various quantum field theory tools with the entanglement entropy to reformulate that discussion as well. So what appears then in this overlap is various theorems, or you can use the tools here of entanglement entropy to gain new insights into properties of quantum field theories or these renormalization group flows in an interesting way. That's a new insight in the past few years. But on the diagram then, there's one overlap left, the one here in the middle. And to talk about that, again, I want to take a step back to this big picture and think about, well, where this story is really embedded in string theory in this attempt to put gravity and quantum together in a single unified framework. So if we think about the renormalization group, well, that's a part of, or that's embedded in quantum field theory up there. And similarly, holography is something that came out of string theory, but it's something that's talking about gravity. And so this part of the story is part of the overlap then between gravity and quantum field theory. Now, the stranger, or the new element in the picture, is entanglement over here, and in particular entanglement entropy. And that's something, that's a tool in this bigger field called quantum information theory. So the new thing, the new perspective that we're getting is one coming from quantum information theory. And so the story I'm telling you is really just a small part of a bigger picture, or what we hope is a bigger picture, where quantum information theory is giving us a new perspective on these two players, which we've been trying to put together or unify for a long time. And the hope is, or the hints are, that perhaps quantum information could be a key to unify these two as we've long sought to do. Now, there have been hints of that, or there have been hints throughout my talk about how space-time, the key player in gravity or in quantum gravity, is related to entanglement. And it started way back when I talked about the Bekenstein-Hawking formula. One of the things I emphasized that this is an entropy that's encoded in the geometry of the space-time. There was also the idea of how various geometric things appeared in quantum field theory calculations of entanglement entropy. And there was this remarkable application of this Bekenstein-Hawking formula in a context where it had nothing to do with horizons or black holes, but in the holographic context, or ADS-CFT context, it was telling us something about entanglement entropy. And so there's really, well, these are some clues in the talk that are connecting space-time, or the geometry of space-time with entanglement. And it's really part of a bigger picture where a slogan that we're using is that space-time is entanglement. And so Raphael's work, original work that I mentioned, was he was actually trying to explain, he was trying to explain black hole entropy in terms of entanglement entropy. There are still some technical issues there, but it's largely believed that the source of black hole entropy, in some sense, is this quantum entanglement entropy. Mark van Ramstonk over at UBC, he's, again, in a holographic or ADS-CFT context, been doing various work saying that the connectivity of the space-time requires entanglement.
What do you mean by connectivity?
How well or how much connection there is between different chunks of my bulk space-time depends on how much entanglement there is between the degrees of freedom describing that chunk of space-time and that chunk of space-time.
This is very, very abstract.
It's very abstract. Why don't you bug me about it at the end? A more concrete, well, I'm not going to tell you what it is. You can come to a talk tomorrow and I'll tell you. I mean, a more concrete realization of this is something that I was doing recently called the space-time entanglement conjecture. And it's basically saying to build a space-time, you need that Bekenstein-Hawking's worth of entropy across, well, between different regions. there are various ideas about connecting anti-de Sitter space or these holographic spacetimes with tensor networks. It's a tool coming out of, a merging of condensed matter and quantum information idea is something called the multi-scale entanglement renormalization ansatz. So that was something developed by Guy Vidal over at Perimeter, and this connection is something that Brian Swingle, now at Stanford, has championed. In the context of black holes, there are ideas coming from Maldacena and Susskind saying that Einstein-Rosen bridges, again, are related to the entanglement between degrees of freedom between the two sides of the black hole space-time. So their slogan is ER for Einstein-Rosen equals EPR for Einstein-Podolsky-Rosen. Again, something you can hear about tomorrow are ideas of in ADS-CFT, where in fact you can ascribe Bekenstein-Hawking's worth of entropy to any arbitrary surface in the interior of the space-time. So that's an idea that came out and has been developed just in the past year. Well, it's actually a work in development still. Actually, now I look at the clock and I see that I've run over. How sad. Okay, so I'm not going to tell you about this. But a slogan at the end of the day is that in general relativity, space-time plays two phenomena, or two roles. It's really a stage on which physical phenomena take place, but it's also really the agent which manifests gravitational dynamics. So it's both a stage and a player in physical phenomena in gravity. And if I had had time, what I would show you, or at least briefly discuss, is that we now have an entanglement interpretation of that. What I had said before is that entanglement sort of is, we understand at some level how this stage arises, or how the space-time emerges from entanglement between various degrees of freedom. What this new work is trying to tell us is that, in fact, the entanglement, or just simple rules about entanglement, are telling us about the gravitational dynamics of that space-time as well. So that's bringing me to the end of the talk, but the big theme, or the big picture to take away, is that there's a new merger. The old merger that we've been trying to build is quantum theory and gravity for a long time. But there's a new player, quantum information theory, which is giving new insights and letting us make new inroads towards that unification. And it may be that in a few years, I can come back and tell you about a new version of quantum gravity called, say, quantum infogravity. But I also wanted to add that these ideas, or this intersection, is also challenging the people studying quantum information in new ways. It's asking, or we're asking, different kinds of questions than they would have asked before. And so it's also leading to, broaden the perspective of quantum information theory and to develop new tools there. And so it may be that in a few years we also come up with a new version, or an improved version of quantum information theory that involves the geometry more and more. And so with that, I will end, and thank you for your attention. Chris.
So to what extent does the precise implementation of these ideas in these various segments require supersymmetry? Like ADS-CFT, is there any precise implementation of that without supersymmetry, or not completely non-SUSY?
The best understood, most well-developed context where that's used is in the context of certain special supersymmetric conformal field theories in 4 and in, I guess, 3 dimensions now. On the other hand, most of the general properties, most of the work in holography or ADS-CFT has nothing to do with that. Typically, it's actually a bottom-up construction where you're you consider different kinds of gravitational theories, and you can understand from various simple properties of a CFT what that gravitational theory has to be like and how different pieces play a role. So supersymmetry really, well, it never plays a role in anything I do, but it's certainly true that, you know, the places where it is on the firmest footing or is best understood are contexts where there is supersymmetry.
And also, could you just say a couple more words about what this means for the infamous information paradox?
Ah, yes. Well, that, I mean, that's I mean, that's a whole other part of this story that I didn't really tell you, but I mean, you may have heard of the firewall controversy. I mean, the string theorists for a long time were very happy. Given ADS-CFT, we thought we understood that the evaporation of black holes had to be unitary, and we had, at some hand-waving level, an understanding of how that should work. What happened a couple years ago is, by thinking about entanglement entropy and thinking about strong subadditivity, what we found, or what folks in Princeton and Samir Mathur, who may have been here, showed, is that actually that picture we had was inconsistent. That the way, it couldn't work the way we thought it would. And so quantum information gave us a more refined probe of the problem and said, we don't really understand what's going on. And so what's been happening in the past couple of years is, well, a consequence of that. But I think it's also by bringing in, I mean, the controversy is not resolved, but much of the discussion involves also importing, you know, this perspective from quantum information theory. I mean, that perspective is really what gave us the problem, or reintroduced the problem. And the hope is that by importing more of the tools, more of that perspective, that we'll understand better how it gets resolved.
Okay, so maybe we can conclude the discussion on the business first. And we're going to take Rob